All right. So problem 1C in this homework problem from 3.2.1. We have d squared y dt squared plus 1 over y dy dt squared. Nonlinear equation because dy dt is squared here, right? Plus is multiplied by 1 over y. Both those make it nonlinear. Equals 0. How in the world are we going to solve that? All our things for linear equations like constant coefficients and Euler equations, like variation of parameters, if there's a f of t on the right, all those things don't apply. There's also some initial conditions. Suppose that y of -1 is 1, and y prime of -1 is, that's off the end, isn't it? Is 1. Both of them are 1, okay. So what do we do with this? We say, well, we don't have any techniques at all that we present in this class because they're so few and far between, except to try a substitution if t is missing or y is missing. Oh, t is missing. So since t is missing, it is not explicitly present, and certainly we're taking the derivative with respect to. So we'll substitute v equals dy dt. And then we'll say that d squared y dt squared is dv dt. Oh, but that's dv dy dt, which is dv dy times v. All right, so I'll make that substitution and replace this one. Say it's equivalently that substitution v dv dy, that's the second derivative, plus 1 over y of v squared equals 0. And now maybe one of our techniques for this first order equation will apply. Well, what does it look like? Well, if I divide that through by v squared, I can get 1 over v dv dy plus 1 over y equals 0, and I could subtract 1 over y from each side, right? That equals minus 1 over y. So I divide by v squared and subtract 1 over y, I get that equation. And notice all I got to do is multiply by dy, and the variables are separated. So 1 over v dv equals minus 1 over y dy, and means I can integrate it and get natural log absolute value of v equals minus natural log absolute value of y plus an arbitrary constant, call it c1. Now we need to solve for v, so we'll take the exponential of both sides and take the absolute value away, obtaining v equals plus or minus the exponential e to the minus ln absolute value of y plus c1. Well, this is plus or minus e to the c1, e to the minus ln absolute value of y. Well, e to the minus ln absolute value of y, put the minus 1 of the exponent, say it's e to the ln of y to the minus 1. And so this is plus or minus e to the c1 times absolute value of 1 over absolute value of y. Right? This is 1 over absolute value of y. And now plus or minus e to an arbitrary constant is an arbitrary non-zero number, right? This can be any positive or negative number. And if you really think about it, you can put in 0, I think, too. Because what we did when we divided through here by v, we assumed v wasn't 0. And so I think v equals 0 is separately a solution to this equation, right? So v equals 0 also works. So this is actually equal to an arbitrary constant, we'll call it C2, over absolute value of y. There's the solution. V is an arbitrary constant over absolute value of y. Well, we could just call it absolute arbitrary constant over y because you can choose C plus or negative. So there's all the solutions. V is an arbitrary constant over y. Now v, we recall was dy dt, that was the substitution. So we're gonna say dy dt is an arbitrary constant over y, which we can separate variables again and say y dy equals c2 dt, and evidently 1/2 y squared is an arbitrary constant times t plus an arbitrary constant. Whereupon I multiply by 2 and square root and get y equals plus or minus square root of twice c2 t plus c3. Well, we could call it c0 t plus c, where c0 is twice c2 and c is twice c3. And so there are the solutions. You get then something that looks like that. Now we've got y of -1 equals 1, means that this has to actually be a positive sign here. So these are all solutions to the differential equation, but to satisfy the first initial condition, y has to be positive, and that radical sign means the non-negative number that has that square root, or that has that square inside. So we now apply y of -1 equals 1. And obtain that 1 on the left is equal to the positive square root. We have to choose to get this initial condition. C0 times -1 plus c. And by squaring, obtain that 1 equals minus C0 plus c. All right. So there's the first initial condition. Then also y prime, according to the prescription there, is again using the plus sign, is 1/2 square root to the C0t plus c to the minus 1/2 times the root of C0t plus c is C0. It looks like that. So there's the derivative. With the second initial condition, y prime of -1 equals 1, tells me that 1 on the left, again for y prime, equals C0 over 2 square, C0 over 2 square root of C0 times -1 plus c. So now we multiply through by this and get see, 2 square root c minus C0 equals C0, and squaring that gives it 4c minus 4C0 equals C0. And what you get in these things in general is two nonlinear equations that can be very difficult to solve indeed. However, we've managed by, right, initially it was nonlinear, by good fortune here, we can actually convert this into a linear equation. Apparently, we've got 4c minus 3C0 equals 0. Now we've got, in this lucky case, it's generally not so fortunate. These are cooked problems, right? Two linear equations that we know how to, and we know how to solve linear equations. Let's see, minus C0 plus c equals 1. Minus 3C0 plus 4c equals 0. And let's see, we could add, we call that equation 1, equation 2. We can solve these by elimination. We could add, what, minus 3 times the first one, so the second one is one way. Obtaining 3 times C0 added minus 3 zeros, 3C0 is 0. Minus 3 times c added to 4c is c. And minus 3 times 1 added to 0 is 3. Apparently c is minus 3. Now we can put it into either equation. So we'll say by equation 1, that looks a little easier. Minus C0 minus 3 equals 1. So let's see, minus C0 equals 4. C0 must be minus 4. I hope I got this right. See any algebra mistakes? So now, we'll say finally, if C0 is -4 and C is -3, doesn't look right here, does it? Y is square root. There's a mistake in computing. Is the square root Oh, look at, okay, minus 4t plus, minus 3. Now you make this positive by choosing C negative. Let's see, if it's -1, then yeah, it is okay, actually. So this becomes 4 minus 3. When t is -1, this works. So apparently we have this solution locally. You notice as t gets to be sufficiently non-negative, when it gets closer to 0, right, that this can become a negative number, and then the solution ends. But locally to the initial point, t0 equals -1. This is then the unique solution of the initial value problem. Hope that gives a nice illustration. What you can see is it's actually not a whole lot of equations we can solve, but these are a couple methods that actually work for a few equations that are easy, right?
And so how do we find the largest interval?
Oh, the largest interval. Yeah, I'm sorry, I forgot that was part of the problem. So there's a theorem there, and the theorem says, and we didn't discuss this much because it's more for math majors. I don't know if some of you are going to be math majors or not, but it is very important to people in other fields too, because again, if you get one of these you can't solve, what do? You run to the computer and run a numerical estimation. It's always nice to know that actually the solution exists and it's unique to this model before you run it and get garbage, right? So I always emphasize that. Interval, what is the interval on which it is the unique solution? There's this theorem here, and this comes out of the notes here. I'm not sure if it's in the textbook or not. Says that the differential equation y double prime equals f of t, y, and y prime, together with two initial conditions, y of t0 equals some number y0, and y prime at some number t0 is equal to some number y0 prime. So that's the value of the derivative. That's the number that's the value of the derivative, not a derivative. Right? Has a unique solution. Remember our theorem for first order equations? When is a first order nonlinear equation, which applies to linear equations, but the linear theorem is better. When is this theorem for nonlinear equations have a unique solution? If I give you this problem, remember that theorem? It says if f and df dy are continuous on the solution interval containing t0, then this has a unique local solution on some interval t0 minus h to t0 plus h, no matter how small, like ordinators of who. But so there's some interval, and there is a theorem where you can get some sort of estimate in some cases, but it's usually not useful. Let's just say there's a local solution on some interval, no matter how small, to that. This has a very similar theorem. This has a unique solution when f df dy and df dy prime are continuous on some interval including t0. On t0 minus h less than t less than t0 plus h for some h greater than 0, provided these partial derivatives are also continuous. So that's what we have to do here, is show that f df dy and df dy prime, when you put the equation in the so-called normal form with the highest derivative on the left, that those partial derivatives are continuous in some interval, then you'll know there's some interval in which this has a unique solution. So we have our problem for t squared y dt squared equals -1 over y. Let's call it y prime squared, just to put it in this notation here. I am actually let's put y double prime here, just to be consistent. So we have this problem, and it says we need call this our f of t, y, and y prime in general. There's no t in this one. That's why we were able to solve it, right? We could use that trick. So this thing, where is this continuous? This one is continuous. So f equals y prime squared over y is continuous because the squaring functions, think of this as a function of two variables, just like from calculus. When is this function of two variables continuous? The squaring function is continuous function of y prime. This is a continuous function, is y itself. Quotient continuous functions is continuous, provided the denominator is not zero. So this is continuous where in three-dimensional space, t, y prime space, y is not equal to zero. So you avoid the y equals zero plane in t, y prime space. Say on one side or the other. And then also we say, well, df dy, partial of f with respect to y. So we're treating y prime as a constant and taking the derivative with respect to y. Then we take y prime squared times minus 1 over derivative of y to the minus 1 is minus 1 y to the minus 2. And so this is the same. This is also continuous for y not equal to 0 because it's polynomial over polynomial, two continuous functions. They're continuous where the denominator is not 0. And then finally, df dy prime is, let's see, right, the derivative of y prime squared is ty prime, treating y prime as a variable. And so you get this, right? Treating y as a constant, you get this, and this is the same, continuous for y not equal to 0. So we just have to watch where y is equal to 0. And so if you were plotting y prime space, y prime, you just have to say on one side or the other of this plane y equals 0. Y equals 0 apparently when minus 4t, so we avoid, according to that solution, we avoid y equals 0, so minus 4t minus 3 equals 0, which is equivalently, let's see, minus 3 equals 4t, so it's t equals minus 3/4. So apparently this then has a solution. We need to include the initial point t equals minus 1 and exclude this point. So it's you get a unique solution. It doesn't. We'll say this and then I'll explain why. There's a unique solution for or on the interval t less than -3/4. Wait a minute. The theorem just says there's a unique solution on some interval, no matter how small. Well, the idea, however, is that if you go over t equals minus 1 a little to the left, and all these are still continuous, then there's a continuous solution through every point you get to that way. And as long as the function doesn't blow off to infinity or otherwise stop, but these things are all continuous, and the function itself has these two derivatives throughout until it's infinity. You can keep every time you run into a point, say, well, here's the farthest interval I can guarantee. Even if it's a limit of intervals, you can say, well, if I take that point, there's a unique solution through there, right? And so that theorem just extends over and over, no matter how far you go, because this is well defined all the way to minus infinity. You say, well, it stops at t equals minus 2. Well, at t equals minus 2, this has a unique solution. And so say it stops at t equals minus 3. Well, it has a unique solution at minus 3 by the same theorem. And so this is actually a unique solution for until you get to minus 3/4 and you get y equals 0, then the theorem fails. And you can see why, right? You start getting square root of a negative number after that. In fact, at minus 3/4, I think the slope is infinite here, isn't it? So, so the theorem makes sense intuitively as well as logically.
So in order to find the interval, we set y, what's inside the t function equal to
You
0?
find the values of t, y, and y prime where f, partial of f with respect to y, and partial of f with respect to y prime are all continuous. treating this as a function of three variables, T1 and Y prime. Any region of three space where the solution stays in that region, and it does, you get a unique solution, because if it stopped anywhere, there'd be unique solutions through that point. Then you apply the theorem again. Right? So you apply it until it exits this region. And in this case, the region was the plane y equals 0, this plane right here. And so the solution runs into it at t equals minus 3/4, and then you don't know if it's. This theorem only says it guarantees unique solution until that happens. Sometimes the unique solution continues even after that point. It's just it's not an if and only. If it's just if these are continuous, then you're going to unique solution. Okay, well, I think that was a really good example. Hope that helps with the other things. I'm also short on time in this course, as you know, so I want to charge ahead the rest of the period. And our next topic is going to be a pretty interesting one. It's Laplace transforms. This is primarily for engineers. Mathematicians do use these certainly plenty, but not anywhere near as often as engineers who love these. These are sort of a quick way to deal with common linear equations and some nonlinear equations that come up in engineering applications, such as electronics engineering particularly. And the Laplace transform is a real interesting thing. Let me put up here. Well, actually, I'll put up the notes first. Let's see. There we go. The Laplace transform method. The Laplace transform, after Pierre-Simon Laplace, I don't know, probably didn't pronounce his name right. Laplace transform of a function f of t defined on an interval that at least includes 0 to infinity. It's just an integral. You call it L of, this is a script L, if you will. A lot of books are starting to put, I think the textbook just puts this as a capital L to avoid this, but in most textbooks, there's some sort of a script L. L of f is equal to the integral from 0 to infinity of e to the minus st f of t dt. So you just multiply f of t by e to the minus st and integrate it from 0 to infinity. We call that the Laplace transform. Can you see what happens when we do that? What happens when we do this? We put in a function of t. There's an s in here that's just a parameter, a constant, if you will. So we get out actually a function of s. We can put in different values of s and get out different results. So sometimes we can put here in parentheses that L of f is actually a function of s. You can put that in if you want, or for brevity, leave it out. People get tired of writing it, so leave it out. But you can also, to indicate that it's in, we'll write script f of s. And so this makes it more plain that you get out a function s. So on the notes, you notice I put up this nice picture here. Oh, wrong screen. I thought that was up, and let's see. Oh, shoot. This one. There we go. So I'll turn the top back up here. Laplace transform method. Here's the precursor, so you know where we're going. Again, look at the model, the picture of the model on the outside before you get all the pieces out. It really helps you to build the model, right? Laplace transform method is an alternative method to find classical solutions to initial value problems. It provides an output versus input transfer function from the engineering point of view perspective. So it allows you to set up differential equations. You put in one function and you get a result. You put another function and you get a result for the right side function. And it can solve some initial value problems that contain functions with discontinuities or impulses. That's one of the big deals out of this. If you look at our other methods we've been doing so far, don't write this down. Suppose I had this problem, y to O prime plus y equals 0. Oh, that's the simple harmonic, or let's say plus some constant times y. This is the simple harmonic motion thing, right? If you put m y double prime plus k y equals 0, that's the mass on the spring problem. So this could be k over m here, for instance, this c. But what if it's not this? There's some sort of function f of t here. The Laplace transform provides a nice way to quickly say, well, if I put in this f of t, then the solution's this. If I put in this t of t, then the solution's that. And you can go quickly between what if I put in different functions on the right as a forcing function. I'm going to drive this now, not just have the mass of the spring, but I'm going to drive it. I can see what the different results are quickly. So that's one of the advantages of the Laplace transform. So the Laplace transform of a function is going to be, of t is going to be a function of s. And what's sort of tacitly assumed in here, but you don't always get it in the textbooks, is that s is actually a complex variable. We aren't going to get into complex variables really for this class. We'll just recognize that actually it can be not real. So there's the definition of Laplace transform. And I drew this picture now, this back down. This is the idea. You put in a function f of t, wave your magic wand, and if you put it in the black box, out of the black box, Laplace transform becomes a function of s. So we can write the script f of s. Let's get the script here on the notes. All right, so we'll say, here it is. And now we can do some examples, for instance, like what is the Laplace transform of the function 1, right? A real easy function. Apparently it's integral from 0 to infinity e to the minus st times 1, right? We know how to integrate that, right? It's e to the minus a constant times t is e to the minus e to a constant times t is e to the constant times t over the constant. And then we just have to evaluate that from 0 to infinity. And as t goes to infinity, assuming s is greater than 0 at least, this decays off to 0, and so we get 0 at the top. And then at the bottom, we plug in 0, and we get e to the 0 over minus s is 1 over minus s. Apparently, the Laplace transform of 1 is 1 over s. You put in 1 into the black box, and out comes the function 1 over s. And you can see also, if you put in a different number, if you put in 4, then you're going to get 4 over s by the same integration. So this is a really useful thing that you want to memorize this result. What if I took Laplace transform of t, right? I put in the function t. What am I going to get out? Well, now I'm going to integrate from 0 to infinity e to the minus st times t dt. And this one we actually know how to integrate using integration by parts, right? If we let t be u, the rest of this be dv, so it's integral u dv, then we'll say du is the derivative dt, right? Is du dt dt following the usual substitution rule is 1 dt, or just dt. And v is the integral of e to the minus st, which we just did, e to the minus st over minus s. So we can rewrite this as uv, let's see, t times v, e to the minus st over minus s, minus integral v du is now e to the minus st over minus s. Du is dt. And we're going to take these both from 0 to infinity. Let's see what we get. Well, at infinity, right, the e to the minus st is a decaying exponential overpowers the t, and you get 0 again in the limit as t goes to infinity. You can use L'Hopital's to prove that, right? I guess I should do the integral first time. So this is minus t e to the minus t e to the minus st over s for the first one. Minus, what's this integral? The minus 1 over s comes out, so you can put this as plus 1 over s. Integral of e to the minus st then is e to the minus st over minus s. And all this goes from 0 to infinity. So now we'll plug in infinity, and this one is 0 because the exponential decays faster than t increases. And this one is also zero, right? The e to the minus st goes to the zero. And then we subtract off the value at zero. And at zero, well, t equals zero makes this equal to zero, but t equals zero makes this 1 over minus s squared, plus minus 1 over s squared. And we get 1 over s squared for the Laplace transform of t.
Quick question,
Yeah,
for that second step in that problem for calculating LT, is the factor e to the negative st over negative s integrated? Or does
Yeah,
it need to be
I'm using
integrated?
this theorem that the integral of e to the kt with respect to t is 1 over k e to the kt plus a constant.
Okay, just ask.
And so I'm just using that with minus s for k. So e to the kt, or e to the kt is e to the kt over k. Yeah, so I'm using that.
And that applies for L to the power of t? Because I'm looking at where it says t multiplied to e to the negative s power multiplied by t minus s minus
No, it's
the,
not, that's not a power. This is t times the quotient. Is that?
yeah, no, what's next to it though? Is that being integrated?
No,
No, not-
this is the integration by parts, u times v, so that's not integrated.
Okay,
Minus the integral v du.
so then what's that weird line that says that it's already been integrated right next to the dt?
Oh, the line means, plug in infinity and plug in, like,
Okay, I've
it's
just
the
never.
fundamental theorem of calculus. I don't want my notation to hold you up. Integral from a to b, is f of t, plug in a and b and take the difference. So it's this line. It's just saying, plug in the top, plug in the bottom and subtract, yeah.
All right,
Sorry about that, yeah. Sometimes it's nice to do it like this. You put brackets around them and then it's more clear. Plus this shows that it applies to both. All right, so let's use the bracket notation. Thank you. And so you get 1 over s squared. Well, you can do this to higher powers too. Right, powers come up a lot in all sorts of applications. And so more generally, if you keep using integration by parts, for instance, if you wanted to take the transform of t squared, you'd have to integrate t squared times this 2 integration by parts. We'll show you the transform of t squared. Right? Each time you do integration by parts, it brings the power down once. And more generally, we can find this, that the Laplace transform of t to the n is equal to n factorial over s to the n plus 1 is what that comes out to be. And so those are 2 special cases of it. So I'd like you to memorize this one and also memorize this one. This is a special case of this one, but sometimes that's not obvious. But we can do some others too. Maybe we can do one more. You want to do one more? And that'll help you for the homework, hopefully. Suppose I wanted to take the Laplace transform of e to the at. Now, all this depends crucially that s is greater than 0. And actually, technically, I've kind of fudged around the fact that s could be a complex number. And then you have to do a little more arguing here. But if the real part of s is greater than 0, then the same result occurs. So, all right. So we'll say, now what's the Laplace transform of e to the at? That means the integral from 0 to infinity of e to the minus st times its function e to the at. And so we can include the integral here. We can say actually the real part of s greater than 0, this result holds. It doesn't hold for all s, but it turns out it doesn't matter, right? So in the complex s plane, it holds in the right half plane where the real part of s is greater than 0. Now this one, integral of e to the at, how do we do that? Well, you can kind of guess maybe. E to the a minus st, right? We combine it e to the at minus st, and there's a distributive property there to write it like that. Well, what is that, I wonder? Well, we can do this fairly easily. This is 1 over a minus s e to the a minus st, right? It's an e to the kt problem. Going from 0 to infinity again. And for real part of s greater than a this time, right? You need this to have a negative exponent in order to say it goes to 0 as t goes to infinity. And so you want s greater than a in order to get a negative exponent. And so this one actually doesn't hold for the half plane s, real part of s greater than 0. What you get now, when you plug in infinity, you get 0. And when you plug in 0, you get 1 over a minus s, which is then 1 over s minus a, right? Minus that is 1 over s minus a. And so you get this theorem that the Laplace transform of e to the at is equal to 1 over s minus a, but this one only applies for real part of s greater than a. And this is sort of technical term. The important thing is to memorize this part. And there's others we can do. Similarly, by integration by parts, again, you can show that the Laplace transform of sine at is a over s squared plus a squared. And the Laplace transform of cosine at comes out to be s over s squared plus a squared. These are worth memorizing too. Some people like to memorize some more, like the hyperbolic function sinh comes out very similarly, a over s squared minus a squared, and this one, the cosh is s over s squared minus a squared. We won't use those so much, so I'll say just memorize these. No Laplace transform of 1, Laplace transform of t to the n, Laplace transform of e to the at, and Laplace transform of sine and cosine. Those are the ones that are used quite a lot. And so there's a table both in the text and in the notes. Here it is, of those functions. I think the text includes a little bit more. I'd like you to know at least these, right? I'll use B here instead of A, but the same formula. All right. Have those memorized. That will help you a lot in solving differential equations if you have that table memorized. Okay. Now, what are some other things we know about the Laplace transform? Here's a wonderful theorem that's really, really helpful. Let's just write a note, actually, because I'm not going to do the proof on this one. But if you have the Laplace transform of f of t plus g of t, something we might write in functional notation like this, Laplace transform of f plus g is equal to f of s plus g of s when Laplace transform of a function f of t and the Laplace transform of g of t both exist. So if the Laplace transform exists, this is true. Can you think what the proof is? It's really trivial, actually. Laplace transform is an integral. The integral of the sum is the sum of the integrals. That's all it's saying. Now you have to include the e to the minus st in there. But when these exist, and that'll exist by the integral of the sum is the sum of the integrals. That's all that theorem really is. But this is called the linearity property. Well, this is part of it. And then the Laplace transform of a constant times f, where again f is a function of t, but c is a constant. It's a number. The constant just comes out because the integral of a constant times a function is a constant times the integral. So these are just calculus results, basically. But they're very useful, so I want to make sure that you're aware of those. So you pull a constant out of an integral, you pull a constant out of this integral. The integral of the sum is the sum of the integrals is all that says. And so between those, we say it has the linearity property that you can do this kind of thing. If you have the Laplace transform of a constant times f plus a constant times g, where f and g are functions, that's a constant times f of s plus a constant times g of s. We call this the linearity property of the Laplace transform. Well, you can just memorize this one instead of these two if you want. This one implies these two, and those two together imply this one. Okay, so there's some of the results we just got. Maybe we should put this one in. What's the Laplace transform of zero? This may be kind of obvious, but if you integrate 0 times e to the minus st, you're integrating 0, and you get 0. So that one's, they never put in the books, but it's actually useful to know that. There's the proofs of all those things. If you want to see Laplace transform of sine and cosine, they're in here. There's your basic properties. Now, when does the Laplace transform apply? And Laplace transform doesn't exist for some functions, right? Because the integrals of some functions don't exist, so it makes sense that the Laplace transform of some functions doesn't exist. This is what I call the famous mean function, right? You take a constant m times e to a constant a times t, a mean function. Then if you have a function f of t whose absolute value is less than or equal to mean, then the Laplace transform will exist, at least for a real part of s greater than a, it turns out. So here's our theorem, or definition and then theorem. We'll say that f of t, a function defined on the interval from 0 to infinity, is said to be of exponential order if for some numbers m and a, positive numbers, it is the case that absolute value of f of t is less than or equal to m e to the at. In other words, if f doesn't grow faster than an exponential function times a constant, then it's said to be of exponential order, right? And then this wonderful theorem, I think we won't prove this one. I think I left the proof in the notes, maybe. Theorem says that if the function doesn't grow faster than the mean function, if f of t is of exponential order, on 0 to infinity, and piecewise continuous. Have you seen piecewise continuous in calculus before? Bring the whole thing up here. I've got the picture here. I'll just run through it here because I imagine maybe you've seen some of it before. A function f of t is piecewise continuous on an interval of real numbers if it is continuous at all but a finite number of points, let's say xk, in the interval, which are such that at each point the function doesn't blow off to infinity but approaches some finite limit. Right? So these are called jump discontinuities. Or if they approach the same number but maybe the function is not defined there, you call it a removable discontinuity. So let me draw a picture here of piecewise continuous. Well, actually, we can put it on the board here because we don't need to draw this for the class. Let's see. Here's an example of a piecewise continuous function on an interval from -8 to 8, for instance. So it starts here, goes over here, and it jumps here, and it's actually equal to this value here, but this is okay as long as the limit at each one is a finite number. And you can have a finite number of these things. Here's a removable discontinuity. If you just filled in the circle, it would be continuous, right? And over here, it jumps down here, and over here, and there's a finite number of jump discontinuities, possibly removable discontinuities. Then it's said to be piecewise continuous, right? Can't blow off to infinity, but approaches a finite limit at each endpoint. And now here's the big theorem for existence of the Laplace transform. I started to write it here. if f of t is piecewise continuous on every finite interval, it can have an infinite number of discontinuities just on every, if you go from 0 to some stopping point A, there's only a finite number of discontinuities. And it's of exponential order, it doesn't grow faster than a mean function. Then the Laplace transform exists for S, real part of S greater than A for some A, or excuse me, for the A that used in the mean function. Right, so let's finish this here in case you want to write it down. But if f of t is of exponential order and piecewise continuous on every interval, 0 to every finite interval, 0 to A for some where A is any positive number. Every interval of this form, then the Laplace transform of f exists at least for, and maybe on other, maybe for other values of s, at least for the real part of f in the complex S plane, where the real part of s is greater than a t function. So this says you can use the Laplace transform for something that doesn't grow faster than exponential. So just for a side note, this means there's a lot of functions for which it doesn't work. For instance, what if I have f of t equals e to the t squared? Does it work for that one? It doesn't. This grows faster than e to the constant times t. E to the t squared is too fast. Doesn't work. The Laplace transform of that one won't exist for any finite, for any region S greater than A in the complex plane. But f of t equals e to the billion t. That's a really fast growing function, right? Has Laplace transform. For what values of A? At least for the real part of S greater than 1,000,000, right? And that's good enough. It's still a half plane, actually, right? So that tells you you can use this for anything that doesn't grow too fast and has at most a finite number of jump discontinuities on any finite interval. Now, see how we're doing for time here. With that, we should mention this. Moreover, I'll go ahead and mention this now, just to be in the order of the notes, although I was going to do something else here. But moreover, if say there is an inverse Laplace transform, we aren't going to do the details of this one because the inverse Laplace transform actually turns out to require a line integral in a complex plane, which is another class. But we'll say it exists such that for any f of s Laplace transform itself with S, we have that L inverse of F gives you back F of T. So the inverse Laplace transform is given this notation, L inverse like that. It's not 1 over L, it's the inverse function, if you will, inverse transform. So whenever you have a transform, you can undo it. And it also has the linearity thing. If you take L inverse of a constant times transform of one function, this being a function of S, plus a constant times another, the transform of another function. This is the script G. I think you guys aren't learning handwriting in school anymore, but that's a handwritten G. Is C1 f of t plus C2 G of t. In other words, the inverse transform of a linear combination is a linear combination of the inverse transform. So it also has this wonderful linearity property. And again, it's because the inverse transform actually is an integral. It's an integral, a complex line integral, it turns out, but we'll say that's a nice property of it. So for example, if I ask you on the homework, what's the inverse Laplace transform of 3 over s squared minus 1 over, let's say 2 over s minus 1. I wonder what that is. Well, we know that the inverse transform of the difference is the inverse transform because of this wonderful linearity property, right? So it's L inverse 3 over s squared minus, and you don't have to write out this step. I'm going to write out in the next step. Moreover, you can pull the 3 and the 2 out. This is actually 3 times the inverse transform of 1 over s squared minus 2 times the inverse transform of 1 over s minus 1. So now I could have done this all in one fell swoop, right? I can pull the constants out and write and undo that. And so that's just this property right here applied, going from here all the way down to here. Now, why did I write it like this? Because I've seen what function has the transform 1 over s squared. What was it? Oh, it was t, right? That was the transform of t. So this is equal to 3 times t, the function whose transform is 1 over s squared, and 1 over s minus 1. 1 over s minus a was the transform of e to the at. This must be the transform of e to the 1t, right? So by our previous table, that's the transform of e to the t. So that by our table, results that the Laplace transform of t is 1 over s squared, and the Laplace put the more general one. Let's just do that one. And the Laplace transform of e to the at is 1 over s minus a. We can infer this. So there's how you can do inverse transforms nicely.
And what page is the table on?
In the notes, well, I can look on the X2 here. I think we put it back behind us here. There it is. It looks like it's on page 194 in this version of the notes. I hope that's the same one I put up. I think so. So 194.
Okay.
All right, now what we want to do is talk about solving differential equations. This is very cool. What it does is it takes your differential equation and it turns it into an algebraic equation. This is the beautiful thing about Laplace transforms. And then you can just do algebra. Here's the next theorem. This one here, Laplace transform of a derivative. And we say if f prime is piecewise continuous on every finite interval and f of t is continuous and of exponential order on some interval t0 to infinity, then you can get this result. So if f prime of t is piecewise continuous on the interval 0 to infinity, well, on every finite interval 0 to a. And f of t is piecewise continuous on every, that's implied. It is of exponential, is of exponential order. On some interval, t0 to infinity, then following result exists, which we can prove here. The Laplace transform of f prime of t, the derivative of a function, is s Laplace transform of f minus f of 0. So there's the theorem for Laplace transform derivative. So how do we prove that? It's not too bad. Here's the proof. Laplace transform of f. Actually, I think it's up here, isn't it? Yeah. Let's use integration by parts. Now let's try that here. Laplace transform of f prime is the integral from 0 to infinity e to the minus st f prime of t dt. Right? Well, if you want to get that prime away, what can you do but integrate it? So what you do is you call this part dv, and you call this part u, and again, we'll use integration by parts, and it has to be uv minus integral v du. This integration by parts, where u is this, so du, the derivative dt is minus s e to the minus st dt, right? And v is the integral of f prime is f, right? So this is actually equal to uv e to the minus st times v is f of t minus integral v du. And this goes from 0 to infinity. Well, actually, plus this is like this. Minus integral v du is f of t s e to the minus s e to the minus st f of t dt, and the whole thing from 0 to infinity, both of these. Well, what's that? This is e to the minus st f of t. Minus and minus is plus, and the s can come out because we're integrating with respect to t. S integral e to the minus st f of t dt. Again, from 0 to infinity. But wait a minute, what's this? If I take this integral from 0 to infinity, that's just the Laplace transform, right? E to the minus st f of t. And so this from 0 to infinity gives you the Laplace transform. And this one at infinity, if this again doesn't grow faster than the mean function, then it'll be overpowered by e to the minus st. And so this will go to 0 at infinity. And so we'll get 0 here and 0 here at infinity, and then minus I'm sorry, not 0 to infinity. So this one at infinity is 0. This one at 0 is f of 0. So plugging in this one, top and bottom, gets 0 minus f of 0. And then on this one, you get plus s, and this is just the integral from 0 to infinity of this, which is the transform of f. So s times transform of f. So this one and this at infinity is 0. This at 0 is minus f of 0, and it's subtracted because it's the bottom endpoint. And so that's the proof then, right? S f of s minus f of 0. Moreover, we can extend that with doing two integrations by parts. Here's the proof for the second derivative. And then you can see inductively, you could say how to take, that there's a similar formula for the nth derivative. Here's the double prime formula, though. You just do two integrations by parts. You do one integration by parts, gives you the integral of f prime times e to the minus st to the second one. And you wind up with the Laplace transform of f double prime is s squared f of s. And so similarly, the Laplace transform of the second derivative, let's call it f, is s squared times transform of f minus s times f of 0 minus f prime of 0 by using two integration by Laplace. And we'll put et cetera because this applies to higher derivatives. However, we're only going to use the first two, I think. You can certainly do the third derivative, s cubed f of s minus s f of 0 minus s squared f of 0 minus s f prime of 0 minus f double prime of 0. So you can see how it extends maybe. But that allows us to solve differential equations. We can use this to solve many DEs, particularly linear ones. That's what this is beautiful for, really. What it'll do is turn a linear differential equation into a linear algebra equation. Here's the formula for general n, right? It's s to the n times the transform minus s to the n minus 1 times the function f evaluated at 0 minus s to the n minus 2, f prime of 0, and so on. And so you've got all those derivatives. Thought I had, where's my example? Oh, it's the next one. Here we go. All right, so let's try this problem for an example. I think there's just enough time to finish this. And then you can try some of the homework. So here's an example. And what you do in these things is three steps. One is you take the transform of both sides to the equation. So we can use to solve DEs in the following manner. One, take the transform of both sides. Turns it into an algebraic equation. So the next step is then to solve the algebra equation. And if it's a linear equation, you get a linear algebra equation, which is easy to solve. Solve the algebraic equation that results. For f of s, the transform of the solution, including what you do is you use the initial values to plug in what f of 0 and f prime of 0, including putting in initial values. Then in step 3, since f of s is the transform of the solution, you just say f of t, let's say DEs in y of t. So the transform of function y of t will be y of s. Let's give it this notation because that's what I'm going to use in the next example. So take transform of y of t, you get a curly y of s as its transform. And then you say the solution. Well, you have the transform from step 2, so you say the solution y of t is just the inverse transform of y of s. Now, generally, you just look this up in a table like we did in that transform. Since we don't have complex line integrals to calculate them. Okay, so it's a 1, 2, 3 thing again. Oh boy, let's leave that up there. So there's my example in the notes. We already know how to solve this one, right? Y double prime plus 3y prime. When we did this one before, in fact. Of 2y equals 0. We can solve this using constant coefficients. Easy, probably easier than this actually. But let's just show that actually you can solve quite a lot of these linear differential equations we've already done using Laplace transforms if you prefer, right? So step 1 says I take the Laplace transform of both sides. Laplace transform of y double prime plus 3y prime plus 2y equals Laplace transform of 0. And here's why I said you need to know the Laplace transform of 0. You get a homogeneous equation, right? So what's the transform of 0? It's just 0, right? So there's that one. If I can erase the end of this just to make some room. Go. And now we expand this, right? The Laplace transform of the linear combination is the linear combination of the transform. So using that property twice, I'll say it's Laplace transform of y double prime plus 3 times the Laplace transform of y prime plus 2 times the Laplace transform of y equals 0. Let's just do it that way. There we go. And now what's the Laplace transform of y double prime? Well, by this theorem here, it has to be s squared times the Laplace transform of y, which is y of s, minus s times y of 0. That's the original function of 0, not the transform. minus y of 0, minus y prime of 0. All right. So there's the transform of y double prime, and then plus 3 times the Laplace transform of y prime by the previous theorem. That's s times the transform of y minus y of 0. All right. And then plus 2 times the Laplace transform of y, just choose the notation, y of s for the transform, and the whole thing's equal to 0. So there's the transform equation. And notice that's actually an algebra equation, right? So that's step 1. Here you solve this algebraic equation. How do you, for y of s, right? So how do I do it? I just group all the y of s terms together, right? Something multiplies y of s. What is it? Well, s squared does. And I better put in what these initial conditions are. I forgot to put those in. This one was this y of 0 equals 1, y prime. So we also had in here y of 0 equals 1 and y prime of 0 equals 0. This is really set up to solve initial value problems. The Laplace transform is it, because as you can see, you have to put in the initial values of this step. So here's the initial values. Y of 0 is 1. So I'm going to put this as 1. Y prime of 0 is 0. This is 0. And this one is 1. So we have s squared multiplying y of s plus 3s multiplying y of s plus 2 multiplying y of s. S squared plus 3s plus 2 multiplying y of s. Plus, what are the other terms? We've got minus s here. Minus 3 here. And that's it, all equals 0. That's an algebra equation in y of s. It's just something times y of s plus something equals 0. Well, this is s squared plus 3s plus 2, all multiplying y of s equals s plus 3. We divide through. And we get y of s equals s plus 3 over s squared plus 3s plus 2. All right, so that's step 2. And now, in step 3, we simply say that y of t, the solution of the initial value problem, is the inverse transform of that. S plus 3 over s squared plus 3s plus 2. And this is sometimes difficult. What you want to do is rewrite that as a function in terms of functions that you recognize as transforms. So I did a little bit of, we're out of time, so let me just shorten it here and say I did a little bit of partial fractions. By partial fractions, here's another application of it, right? You can rewrite this quotient as 2 over s plus 1 minus 1 over s plus 2. So by partial fractions, this is just algebra here. 2 over s plus 1 minus 1 over s plus 2. Partial fractions from algebra. You can do that on your calculator with the expand function if you want. Although little partial fractions is a good idea now and then to keep your skills up. And now we know that the inverse transform of the sum is, and the linear combination is linear combination of transform. So this is twice the inverse transform of 1 over s plus 1 minus 1 times the inverse transform 1 over s plus 2. What's the inverse transform of 1 over s plus 1? We remember this property that Laplace transform of the e to the at is 1 over s minus a, right? We'll use that here. This is 1 over s minus a negative 1, so it's the transform of e to the negative 1t. This is this is 1 over s minus a negative 2, so it's the transform of e to the negative 2t. There it is. That's the solution of the initial value problem. If you would have used the characteristic equation, r squared plus 3r plus 2 equals 0, you would have got r equals negative 1 and negative 2. Plug in the initial conditions, you get the C1 and C2 are 2 and negative 1. All right, time to get out of here. Let me leave you with some things to look at then. Boy, out of the notes, look at section 3.2.1. Did I give you that one last time?
You did.
Yeah, 3.2.4 that I'm giving you here. Look at 1, 2, and 3. Make sure I'm in the right section here. Yeah, okay. And those are Laplace transforms and inverse transforms, and then 3.2. Oh, geez,
Isn't,
3 point, no. Should be 3.4, 3.4.1, I wrote it down wrong. All right, 3.4.2. Numbers 1 and 2. These are on, I think on the. Then out of the text. Take a look at the 6.1.5. This will give you a lot of Laplace transform examples. 6.1.5 to 6.1.15, I guess that is. Try those for now, and that'll be plenty. On Monday, I'd like to give an extra credit problem. Maybe instead of Laplace transforms, let's just do it on the mechanical vibrations, right? The applications. So if you study for Monday, I'll give you 5-point extra credit somewhere in class to do on the mass on the spring or the LRC circuit. One of those two. Okay. See you tomorrow.
are you going to be available after class, Professor?
Yeah, I have another class at 11, but I'll be available